In lecture 21, we're going to look into pick instruction set. Just again, a reminder, homework is due today, and we're going to have the exam tomorrow. We talked about opcode and also a little bit about instructions. For the pick 16F 1829, it has 49 different instructions, and each instruction is 14 bits. Now, note here it's not 14 bytes, it's 14 bits. It has three categories of instructions: byte-oriented, bit-oriented, and literal and control. Let's start with the byte-oriented instructions. This particular PIC microcontroller is an 8-bit controller. That is to say, the data size that this microcontroller deals with is 8-bit, or a byte. And that's why this byte-oriented instructions is for manipulating, doing the computation or logic operations on these byte-wide operands. The general format is like this: opcode, then F, which represents some register or some operand, then comma, then this F or W. We're going to see many of these F and W a lot in following slides. I'll explain in more detail what they are. The opcode is basically the mnemonic. For example, subtraction or addition, so we have SUB and ADD. So this is what we call opcode, the operation of this instruction. F is the source operand. It's a name of an FSR or a RAM variable. So essentially, it's a name of a register or the address, the offset of a variable that is in the data RAM. Then this F or W, you can only have one of them in the instruction. So you can have F or W, but not both. This is literally a letter you need to use. It's not a representation or placeholder. It's exactly the value you will put there. It's either F or W. And this letter here indicates where we want to store the result. This is to tell the microcontroller where the destination is going to go. If this letter is F, that is to say the destination is to be the same as the source register. So F here, this register is going to be both the source and the destination. If we choose to say comma W, then W is the destination. And in fact, this W is the working register we mentioned earlier. Remember, the output from the ALU goes directly to the W, and this is the W. So if we have a letter here, say W, that is to tell the microcontroller this operation, once it's completed, the destination, the result should be put into the working register, W. And figure on the right, on the top right here, this is how the PIC microcontroller encodes such a 14-bit instruction. If you count the number of bits, you start from 0 all the way up to 13, so total 14 bits. And that's this 14 bits. So this is one instruction. Opcode will take 6 bits, okay, from 8 to 13. So this 6 bits tell you what kind of operation this instruction is trying to do. The lower 7 bits, from bit 0 to 6, we have 7 bits here. These 7 bits are the offset in the direct addressing mode. Remember the figure we just explained? in the direct addressing mode, how you get these 7 bits and 5 bits. 7 bits, the offset to a byte in a bank, comes from the instruction. This is where they come from. These 7 bits are encoded into the instruction. Now this bit 7, this D, just 1 bit. It's gonna indicate the destination. And that's really how we encode this F or W. If it is a 0, that is to say the destination is going to be in the working register. If this bit is a 1, and the destination is going to be in the source register. So depending on the F or W indication you have in an instruction, this bit will be either 0 or 1. Because the bottom line is, eventually the microcontroller will need a machine code instruction like this to perform the operations. So this F or W in the assembly language code will eventually be encoded as a 0 or 1. The second category of instruction is so-called bit-oriented instruction. It has opcode, it has a source operand, and then it has a bit address. Since every operand is a byte, we're talking about bit locations from 0 to 7. So the second operand here for this bit-oriented instruction has a range. The valid range is from 0 to 7 inclusive. And to encode such kind of instruction, the PIC microcontroller uses this format. The upper 5 bits, actually 4 bits here, are for the opcode. And then this here we have 3 bits, and these 3 bits are for the bit address, because 3 bits will give you 8 possibilities from 0 to 7. And the lower 7 bits are again used for the offset within a register bank. The last category we want to talk about include this literal and control. Basically, it has an opcode and then some literal value. This literal value, you can just understand this value as a constant number. The general format is opcode and 8-bit literal. For call and go to instructions, the size of the literal is different. In this case, it has 11 bits, and then the opcode has 5 bits. Other instructions, for example, move, relative branch, and the FSR instructions used in the indirect addressing mode, also listed here, but I will not go into more details. RAM variables. We know this RAM here refers to the data memory, and memory variables are the symbolic names to refer to space in the memory. For this particular PIC microcontroller, the usable space is from 20 to 7F. We're talking about the locations within the bank. So the maximal address here is 7F. The locations lower than 20 hexadecimal, those are used for reserved registers. And these registers all have special names. From this 20 to 7F, these are the registers you can use as a general purpose registers. For example, for your computation, you can use them as a temporal variable to do the arithmetic or logic operations, things like that. Let's look at this following example. Here we have two keywords, C block and NC. C blocks 20 hexadecimal, variable 1, variable 2, variable 3. Then NC. This C block and NC pair is used to declare variables in memory. And also you assign symbolic names to these variables. What this example is going to do is it's going to allocate 3 bytes starting from address 0x20. So this first variable, variable 1, will take address 20. The next one, variable 2, will take address 21. Then variable 3 will take address 22. So this is not an instruction, by the way. This C block and C, you can think about them as a pseudocode. They just help the assembler to know that later in the program, whenever I use variable 1, this in fact refers to address 20. Whenever I use variable 2, that is in fact address 21. So instead of using these exact values, addresses in our programs, we can refer to them by using the symbolic names. So it's like you in your C code, you declare integer A, B, and C. But in this case, we need to tell the assembler where they are located. And this is the 020 is for. Of course, you don't have to start at 020. You can do 0x30 or 40, etc. This table and the next one just gives you the list of the instructions we're going to look into in our class. Not necessary today, but we'll definitely look at these instructions. The assembler will most likely give you warnings or even just errors to prevent you from allocating more than it has. Now we're going to look at the real instructions. We start from these clear and move instructions. The first instruction, clrw. CLR, clear. W. These 4 letters are one upper code. They're not separated by spaces. This clrw with no operands, you see. This instruction is to clear the working register. So W is a special register, and we can clear it. That means we're going to assign 0 to this register, and that's what this is for. Similarly, we can clear other registers by using clrf and then f. This f here, this lowercase f here, is a placeholder which has to be replaced by a real variable or location. Now, using the example of the block, so we declared variable 1. So what we can say here is we can do clear f variable 1. So that location will be cleared. Next instruction is move LW and then K. Okay, so the way you understand or try to figure out the operations of pick instructions is by really try to find the keywords in it. MOV is a move. This L if you see L in the opcode, this stands for literal or a constant number. W is the working register. This instruction takes one operand, which is K, and K is a literal value. So it could be a 1 or it could be 34 in hexadecimal. So this will be a byte, a constant number. What this instruction will do is to copy that value to working register. So that's move literal to the working register. And what value you want to move in? This K. Next instruction, move WF. Can you guess what this instruction does? Well, even though it's explained here. But this is a move instruction again. We're going to move the value from W to F. Now, F is just saying the operand needs to be a register. And this F is the real register. This is the destination. So we're going to copy the value from the working register to this one. So you can use variable 2. So in that case, you're going to copy the value of W to variable 2. The next one, move F, comma, FW. Okay, let's look at what this instruction is trying to do. This again is trying to do move or copy. F, that is to say, you need to have a register as the operand. So let's say we do variable 3. The real F here is variable 3. Okay, it's to move F, variable 3, comma, we can choose either F or W. Let's say if we choose W, okay? So let's say we have a move F space variable 3, comma, W. So what is that instruction it's going to do? It's going to copy the value from variable 3 to the working register, W. Okay? Makes sense. Now, what if you have move F, variable 3, comma, F? We explained earlier that when we see a F instead of W, that is to say, the destination is the same as the source. And since this is the move instruction, what the microcontroller is going to do is to copy the value of variable 3 to itself. Seems doesn't make sense, right? Why do you need to copy the value to itself? What was your question? Uh-huh. So the reason we have this uppercase F and lowercase f, it's just trying to tell you that they mean different things, but in reality, in PIC microcontroller assembly, it's a case insensitive. So the particular example I use is move F VR3, comma F. So it looks like we're going to copy the value of variable 3 back to itself. This is a valid instruction. From the first looking at this instruction, you may think this is not useful because you're not going to change the value of that variable. However, this move F instruction will update flag bits. It's different from the x86, where move instruction does not update the flag bits. Here it does. So you check whether the value of variable 3 is 0 or not. And this is the way you can do a conditional branch after that. We'll talk more. The last instruction is swap f. So you're going to swap the upper 4 bits with the lower 4 bits of the register and put the result into the source register, source operand, or the working register. Let's go through the following examples. clearf temp 1. Let's assume this temp 1 is declared in one of the C blocks. Okay? So clearf temp 1 is going to put 0 into this variable. Move lw5. We're going to load 5 into the working register. Move wf temp 1. So we're going to copy the content of w into a register. That's what this f is saying. And that register is temp 1. Next instruction. Move wf temp 1, comma f. This is in fact a incorrect or invalid instruction because move wf has no destination indicator needed. Because the direction is very clear. It's going to copy from W to F. Next instruction, move F, temp 1, comma, W. So we're going to copy the value of temp 1 to the working register because of this W. Next instruction, move F, temp 1, comma, temp 2. This is incorrect. This is the invalid instruction because for move F, the second operand is either F or W. You cannot copy the value directly from one variable to another variable. Ever. If you want to know why, you want to look at the diagram when we explain the internal structure of the PIC CPU. The output of the ALU is to W, and the input, two inputs to the ALU, one has to be W. Swap is to swap the 4-bit nibbles of temp 1. And by using W, that is to say, I want to move the result into the working register, but without change temp 1. Single bit manipulation. So these two instructions belong to the bit-wide operations. Bit clear a register. So we're going to clear one bit of a register. And the register is given here, F, comma, B. This BCF space F, comma, B. This is just a template. BCF is the one you need to use. This F will be eventually replaced with a real variable, either name or address. And this B, lowercase b, has to be a number from 0 to 7 because we only have 8 bits. So BCF will clear bit B of register F, and on the opposite, BSF will set bit B of register F. We have two examples here. BCF port B, comma 0. This is to clear bit 0 of port B. The second example is BSF status, comma C. This is to set a bit in status register. Now, what is C? C, we tell you that this is the carry bit, but in fact, C is declared as a constant by the assembler in the header file, because we know in the status register that bit, I think it's bit 0 or 1, that's the carry bit. So we just use C to represent that. So the bottom line, this C is really a number, and that is the index of the carry bit in status register. Similarly, you can do Z, as you say that's the 0 bit. Yeah, that's the same effect. Now let's look at this example. Show the values of all changed registers after the following sequence. So in this short program, we begin with C block and C. And there we declare two variables, and you know where they are. The first instruction is clrw, and then move wf x, and then move lw 0xfe, then move wf y, and then swap f, then bcf, bsf, then move f. So I'll give you 1 minute to work on this example. Your task is to show the values of all changed registers after the following sequence. Okay, let's look at the solution. Clear W is to put 0 into the working register. Then the next instruction is move WF. So we're going to copy the value from working register to a register. And that register is X. So X will have the same value as W. Next instruction is move LW. This is the literal. We're going to move the value, a constant number, to the working register. So basically we assign value FE in hexadecimal to W. Then followed by the next instruction, move WF. So we're going to copy the value from the working register to Y. Then we're going to swap F, and the operand is Y, comma F. So the source is Y. Okay? So we're going to do the swap, the upper 4 bits and lower 4 bits of Y are swapped. And this destination, because we have F here, that's to say the destination is the source. So we're going to use Y to store the new result. So this instruction will change the value of Y. So Y now have EF in hexadecimal. BCF Y, comma 3. So we're going to clear bit 3 of Y, and if we write down the initial value of Y in binary, this is 1110, 1111, and we clear that, so this 1 will now become 0, so the result is E7. Then we do BSF X, comma 3, which will set bit 3 of variable X. Okay. So this will become a 1. So the value in X will be 8 in hexadecimal. The last instruction is move F, Y, comma W. This is to copy the value from the source, and W indicates the destination is the working register. So we're going to copy the value of Y into W. So W will have E7 in hexadecimal. Three new instructions: increment, decrement, and complement. All of them take the similar format. So the upper code, the register, comma, and then F or W. You choose either one. And their operation is simple to understand. INC is for increment F, and DEC for decrement F. And complement is basically doing the NOT operation of F. And depending on the destination indicator, the result could be in source operand or in the working register. It will update the status Z. Let's just take one example. Comp F temp 1, comma F. Comp is complement, and the source is temp 1. So we're going to change zeros and ones to ones and zeros in temp 1, and because the F, so the new result will be put back into temp 1. It's just the opposite, do a NOT operation. Then addition and subtraction instructions will add LW. That's to say, I want to add a number with W, and K is the number. We can do add WF. That is to say, I want to add the value in W and register F. The sum of these two numbers will be put into either the register itself or in the working register. So we have the option here. For subtraction is similar. So we have sub LW and sub WF. Let's take one example here. ADDWF temp 1, comma F. This is to say I want to do the addition on two numbers. One is in the working register. The other one is in a general purpose register, and that is temp 1. This comma F to say the sum of these two numbers will be put into temp 1. So this is the operation. So temp 1 plus the working register, and sum will be put into temp 1. Any questions? Okay, now let's work on this example. We declare three variables A, B, C using C block. And then we have these following instructions: clearf, and I have INCF, subtraction, addition, and so on. So I'll give you 1 minute to figure out the updated content of these variables. Okay, let's look at the solution. The first three instructions just put zeros in these three variables. Then INCF, variable A, comma W. So we're going to increment the value in variable A, but the result is going to be put into the working register, W. So as we see here is variable A plus 1, so 0 plus 1. That is 1, and W will have 1. Then sub LW. So we're going to subtract literal, okay, and the other operand is W. So what we're going to do is we're going to use this literal value, this number F, subtract W from the number. So we do the literal value minus W. So that is F minus 1, that's E. So W will have the new value, E. Then we do addition. Add WF. It takes two numbers. One is variable B, that's given here. The other operand for the addition is the W. So variable B plus W, that's E. And because of this F, so the result, the sum of these two numbers will be put into B. So variable B will have E in hexadecimal. And then we do decrement. We decrement variable B, and because of this F, so the result will be put into variable B. So that's why we have E minus 1, that's D in hexadecimal, and put it back to variable B. Next instruction, we do complement, and the register used is variable B, so we do a not on variable B. And because of this W, that is to say, the result will be put into the working register. So W will now have the not on this B, so that's F2 as the final result. The last instruction is subtraction, WF. So we're gonna do this variable C minus W, and this difference will be put into variable C because of this F.